Welcome to today's lecture. Today we are going to discuss message passing paradigm for distributed memory systems. In previous lectures, we have already covered the topic of shared memory systems, and you did several assignments using APNMP on shared memory systems. So we see that there are different kinds of models based on different kinds of architectures. There are three primary aspects on which these different models differ from each other. So the first one is the view of the address space. The second one is the degree of synchronization imposed on concurrent activities, and the third one is the multiplicity of programs. The most important feature of message passing paradigm is that it is primarily based on a partitioned address space, and we need explicit parallelization. So that makes it little bit more difficult compared to the shared memory system parallelization. First, let us give me an overview of the topics which we are going to cover in this particular topic. So first, we look into the differences between a distributed memory parallel computer and a shared memory parallel system. Then we are going to talk about the message passing programming model and the protocols. Finally, we'll focus more on the MPI, message passing interface. We'll discuss this topic using an example. Then we'll discuss in more details regarding the MPI communications, and we can do a couple of case studies using MPI. So, first, let us try to understand the major differences between a distributed memory computer, which is depicted on the left side. So this is a distributed memory computer, and let us see how does it differ from a shared memory computer. So first, let me discuss the shared memory system, because you have a good understanding of this system, and you have done several assignments on this kind of system using OpenMP. So, if you look into a shared memory computer, the main feature of this kind of machines is the shared address space. So, you can see there is a common data space that is accessible to all processors. So, here the processors are represented using P1, P2, P3, Pn, and the C's represent the cache which belongs to each of these processors, and then you can see the memory. So although these are represented using m1 to mn, but you can see that they are combined using this dashed line. So there is a common address space which any of these processors can access. Now if you compare this with a distributed memory computer, here you can see that each processor, that is P1, P2, Pn, each of them has an independent memory. So that is local to this particular processor. And if the processor P1 wants to access the memory of processor P2, then it has to do that explicitly by using a communication network. Now, if you look into this architecture, that is the shared memory system, we also refer to it as uniform memory access, although we can say that processor P1 can access its own cache much faster compared to processor P2 accessing C1, that is the cache of processor P1. But let us assume that we do not take into account the cache, but if we just talk into this global memory space, that is a big common data space which is being accessed by all these processors, then the time which is required to access this memory space, this common data space, is same for all processors. So that's why we call it uniform memory access multi-computer. But if you look into a distributed memory computer, then the time which will be required by P1 to access M1, that is its own local memory, will be much less compared to accessing the memory of the other processors which are in that particular system, and therefore we refer to is at non-uniform memory access. Okay. Now, with this understanding, we can go forward and we can see how to program or what are the important protocols which we need to understand to work with distributed memory computer. As discussed in previous lectures, that it's very important to recall that the data which flows from the processor, basically which flows from the memory to the processor, it follows a path. So it first comes from memory to the cache and then it goes to the processor. So the performance of a code very much depends on how good we can optimize this whole flow, that is from memory to cache to processors. And it we have also discussed that how performance depends significantly on the reuse of data in cache, and also the size of the cache also matters. We can discuss more about the caches in one of the future lectures. So let us go and once again look into the major differences between a shared memory parallel computer and a distributed memory parallel computer. So as we have discussed, in case of shared memory parallel computer, these processors can access all memories. In case of distributed memory computer, processor can only access local memory. It can access the remote memory, but that will require explicit communication. Okay. So that's why we need to make sure that these memory accesses which takes place through explicit communications needs to be done properly, and certain protocols needs to be followed. uh, in case of shared memory systems, processors are generally all same and have equal access to machine resources. So, and we also call it symmetric multiprocessor. In case of distributed memory computers, all processors may not be same. You can connect different kinds of processor through those communication networks, and you can make a cluster out of that. As we discussed earlier, that shared memory computers generally fall in case of, I mean, in the class of uniform memory access machine, whereas distributed memory systems, because the access time to memory location is not uniform, they are also known as non-uniform memory access machines. Now, since as we have seen in the previous slide, if we go back here, this communication network plays one of the major role, and it determines how efficient your program is. So the access time to memory location, the access time to the memory of another processor depends significantly on the network connection. So you can say that the network connection plays a crucial role to the determining the performance of a given code. And ideally, we like to have a low latency, high bandwidth, specialized network connection. The advantages of distributed memory systems are that they are highly scalable, because each processor has its own memory. So, as such, the memory contention problems are less compared to shared memory systems, where, as we have discussed earlier, there are chances of race condition. So, that is relatively less here. Now, let us look into the different kind of parallel computing paradigms. So, in case of shared memory systems, we have already used OpenMP, which is a directive based paradigm. Similarly, we are going to, particularly in this lecture, focus on message passing interface, which we are going to use for distributed memory systems. But the advantage of this particular paradigm is that it can be used for both distributed as well as shared memory systems. And that makes it very much acceptable to the programming community. We can also discuss about multi-level or high-bit parallel programming, so which is a combination of message passing interface and OpenMP. So basically, we are trying to combine both the paradigms together. I mean, shared memory and distributed memory parallel computing systems. If you remember, there are three levels of parallelism. So the first one is like instruction level, the second one is thread level, so that is basically what you learned while doing shared memory programming, and the third one is the node level. So when you combine all these things together, so that is instruction level, thread level, and the node level, that is something which we can refer as hybrid parallel programming. Before we go into the details of the protocols which are associated with message passing paradigm, let us look into these two different models that we call SPMD and MPMD. So SPMD is basically a single program that performs same operation on multiple sets of data. So basically, you have a single A dot out or executable. In case of multiple program multiple data, so you basically have different programs which perform different operations on different sets of data, and a hybrid program is one in which some processes perform same tasks and others performs different tasks. To understand it in a better way, let us look into these small code snippets. In case of single program, multiple data programming model, all processors execute same program. So basically, you have the same A dot out, and they work on different data sets. So basically, we are referring to domain decomposition. So suppose you have a ID that is like K. So if you just put some if else statements that if the ID is this, then this particular process is going to work on that particular data set. If the ID is K plus 1, then that particular process is going to work on a different data set. But when you look into the multiple data programming model, different processors execute different programs on different data. This can also be looked in the form of a master slave model. So, master CPU basically creates and dispatches jobs to slave CPUs running a different program. And so suppose the process ID is 1, then you have a different A dot out, and then you can have a different A dot out for a different CPU. This can also be converted into a single program multiple data model. So we can write it like that: if the CPU ID is 1, run program 1; if CPU ID is 2, run program 2. Basically, in this lecture, we'll be focusing more on the single program multiple data models. So, what are the primary rules as far as distributed memory computer is concerned? The first rule is that problem needs to be broken up into independent tasks with independent memory. So, each task is assigned to a processor. We have already looked into the process of domain decomposition. So in this case also we are going to perform domain decomposition. But what is important to be noted here is that these independent tasks have independent memory. So they're broken up into independent tasks with independent memory. That's the major difference when you compare it to this shared memory system. Now, in message passing paradigms, we are talking about message. So this message exchange takes place explicitly. So basically, what a message is that we need to understand. So these messages are basically some kind of data, and they are transferred explicitly using explicit instructions, and we need to understand how to optimize these communications. So we'll go into the details of message passing interface. So it is something similar to OpenMP. So it's basically library of subroutines and functions. It's not a language, and programmer insert appropriate MPI subroutines at appropriate locations, function calls, compile with special flags, and finally link with message passing library. So what is a message? So message is basically a collection of data. It consists of basic data types such as integer, float, real. It also consists of derived data types. And the second part is the message envelope, which basically consists of some particular information like the source, the destination, some kind of tag, the communicator. These things will be more clear as we go forward. Let us quickly summarize the advantages of MPI. It provides efficient communication among cluster of nodes, helps in more analysis in a given amount of time, because you can have as many processors as possible in a given distributed system, reduces time required for one analysis, and the one of the major advantages, like you have access to more memory. So you can, the combined memory coming from different systems can lead to a huge memory. And to enhance the code portability, I mean, it's very, very portable. So this MPI model basically works on both shared as well as distributed memory systems. What are the limitations? It introduces an additional overhead because there is a communication network which is present, which is basically inter-processor communication, and this low latency, high bandwidth for inter-processor communication. This particular requirement is very important to have high performance. So, to summarize what we have discussed till now, so we are talking about a model which we call message passing model. So here the data exchange takes place explicitly through communications. Uh, this message passing interface model works for both distributed as well as shared memory parallel machines, and the programmer or the user has full control over the data partition distribution, and the programmer is responsible for identifying parallelism and implement parallel algorithms using MPI function calls. So the debuggings are a little bit difficult compared to shared memory systems, because the programmer needs to identify the parallelism by I mean himself or herself. So it's not like an auto parallelism. Okay, so now we can first discuss the major protocols which are involved in message passing programming. So we can also call it the principles of message passing programming. So message passing programs are often written using this asynchronous or loosely synchronous paradigms. So if you remember, in synchronous paradigms, a task need to wait. So it is basically in synchronization with other tasks. In asynchronous paradigms, these tasks are more or less independent. So they did not need to wait for other tasks to complete. And loosely synchronous paradigms are somewhere in between synchronous and asynchronous paradigms. So, if you look into an abstract or a logical view of a parallel machine supporting the message passing paradigm, let us assume that it has P processes, and each of these processes has its own exclusive address space. Each data element must belong to one of the partitions of the space. Let's say there is an array A 1 to 100, and say there are 10 processes. So you can say that 1 to 10 belongs to process 1, 11 to 20 belongs to process 2, and so on. So each process has its own exclusive address space. So if process 1 wants to get say A 15, then it needs to communicate with process 2, and that communication has to take place explicitly through some kind of a communication network. So that is the second point. Each data element must belong to one of the partitions of the space. Hence, data must be explicitly partitioned and placed. All interactions, read only or read write, require cooperation of two processes: the process that has the data and the process that wants to access the data. So let us look into this basic message passing process. So the most important message passing process is the send receive. So suppose there is a process 0, and there is another process which is process 1. So process 1 needs some data which is not present with process 1, and that data is present with process 0. So what means is that process 0 needs to send that data to process 1, and process 1 has to receive that data correctly. Now there are several issues which comes into play, like who will send data, to whom the data is sent, who will receive the data, because if there are several processes, these things needs to be clarified before this whole send receive mechanisms starts. So you need to be very clear who is going to send the data, who will receive the data, where is the data present, what type of data, and whether it's an integer, it's a float, what kind of data, how much of data, whether it's in bytes or kilobytes or megabytes. And the most important thing is that how do we make sure that the send receive has been completed successfully? Because we can always send some data, but we have to also make sure that it has been received in the form in which it is supposed to be received. So it does not receive a value, something other than what has been actually sent, or it does not, a process does not receive a value which was not meant for that particular process. So as I was discussing, that message passing programs are often written using the asynchronous or loosely synchronous paradigms. So in the asynchronous paradigm, all concurrent tasks execute asynchronously. So they basically do not depend on each other. So suppose there are two tasks, they are not in synchronization each other. So one can go ahead without being informed about what is going on in the other task. In the loosely synchronous model, tasks or subset of tasks synchronize to perform interactions, and between these interactions, tasks execute completely asynchronously. Um, in the synchronous model, there is a lot of idling time involved because one task always need to be in synchronization with the other tasks, and it needs to wait. If the other task is not completed, then it needs to wait and make sure that other task also gets completed before it can go ahead. So most of the message passing paradigms are written using the single program multiple data model, which you have discussed earlier. So let us look into let us look into the message organization in MPI. So message is basically divided into data and envelope. So data has basically three components: the buffer. We'll discuss what exactly a buffer is. The count, how much data we want to send, and the data type, what kind of data it is. The envelope basically consists of the process identifier. So, what is the source of the data and where it is supposed to go? So, the rank of the source and the destination. Some kind of message tag. So, suppose two messages are being sent between the source and the destination. So you can identify those two messages by using distinct tags. So let's say we give a tag of 1 to the first message and a tag of 2 to the second message, and we can independently verify whether the first message communication has taken place successfully or not, what happened to the second message, and so on. And then there is a communicator, which we'll discuss later as we go forward. And this message passing interface follows a particular order for these attributes like count, data type, destination, tag. Once we understand the protocols, then we can look into the details of these arguments. So let's first look into a typical send and receive operation. So we may call it the building block of message passing paradigm. So if you look into the send operation, so you can see that the first argument is like some kind of a send buffer. Then the second argument is like how much you want to send, the number of elements, and the third one is like the destination. Because when you are sending from the source to the destination. So in the source process, you are just mentioning about the destination. In the destination process, so destination is basically receiving the data. So what we need to mention in addition to the first two attributes, which are like the receive buffer and the number of elements, the source identifier, so from where the data is coming. Now let us consider this simple example. It might look very simple, but there are many questions which are associated with this simple code. Let's say that the process 0 has a variable named a, and the value of that particular variable is 100, and this process P0 wants to send this data to process 1. So you can see 1 here, and then once this is completed, then process 0 will change the value of a from 100 to 0. Now process 1 is supposed to receive this data. So basically, if you look into the step by step process of this sequentially, this process 1 should actually get a is equal to 100. Now the question is, what if process 1 gets 0 instead of 100? Okay, so the semantics of the send operation requires that the value received by process P1 must be 100 as opposed to 0. But now suppose before this message actually reaches P1, it gets replaced with the value of 0. So instead of getting 100, it might get 0. So this kind of questions actually motivates the design of the send and receive protocols. So buffer is basically some kind of user defined variable. It can be array or a structure. So MPI system memory, it's a kind of a memory used to process data, generally hidden from the user. We basically pre-pack the data which you want to send and put it in the buffer. Now there are four primary protocols. So we call it non-buffered blocking message passing operations. Then there is buffered blocking operations. Then there are non-buffered non-blocking operations and non-buffered blocking operations. Okay, now let's first look into the blocking non-buffered send receive, or let's say non-buffered blocking message passage interface. So the dilemma which you were facing in the previous example, that we want to send 100 and we want to make sure that process P1 really receives 100 instead of 0, and we have to make sure that when it is safe for the send operation to return, so that the semantic is correct. So this does not mean that send operation returns only after the receiver has received the data. So what we mean to say is that we want to make sure that sending operation blocks until we can guarantee that the semantics will not be violated on return, irrespective of what happens in the program subsequently. So you just want to make sure that the semantics remain correct. It does not mean that the send operation will actually gets blocked. If send operation can guarantee that the semantics will remain correct, then it can return. So in the first case, a simple method for forcing send receive semantics is for the send operation to return only when it is safe to do so. So in the non-buffered blocking send, the operation does not return until the matching receive has been encountered at the receiving process. So if you look into this particular example, so basically this is the send operation. So unless this is received by process P1, it will not proceed to this operation, that is a equal to 0. Now the challenges which are coming is like what if the receive does not occur exactly immediately after the send of operation has been initiated. So there can be a lot of idling time because we are blocking this particular operation here. So idling and deadlocks are major issues with non-buffered blocking sends. Basically, we are blocking the CPU. We are not letting the CPU to go ahead unless we make sure that it has been received properly by the receiving processes. In buffered blocking sends, so till now we have discussed the non-buffered blocking paradigm. In the buffered blocking sends, the sender simply copies the data into the designated buffer and returns after the copying operation has been completed. So that data is copied at a buffer at the receiving end as well. So what we can say is that buffering reduces the idling at the expense of copying overheads. Now, how this buffering takes place? I mean, if you just look into this example, it might look like it's easy to ensure that the send and receive operations are done correctly, but we need some hardware support to do that correctly. So, most message passing platforms have additional hardware support for sending and receiving messages. They may support direct memory access, we also call it DMA, and asynchronous message transfer using network interface hardware. So basically, network interface hardwares allows the transfer of messages from buffer memory to desired location without CPU intervention. So let us understand this point clearly. So here there is a CPU intervention. So A is equal to 100, then CPU is responsible to make sure that the data is sent, and then CPU is responsible for again converting that A from 100 to 0. Now, when we are talking about the supporting hardware, so what this network interface does is like it allows the transfer of message from the buffer memory to the desired location without CPU intervention. So the CPU simply copies this to the buffer, and then it did not worry. From buffer, it will directly reach the receiving process, that is P1, without CPU intervention. So basically CPU can is now free to do whatever it can do in the next I mean syntaxes, whatever is there, like next command is A equal to 0. So basically CPU just copies that data to a buffer, and then the copy from the buffer to the receiving processes is taken forward with the help of this special hardware, that is this network interface or direct memory access. So direct memory access also allows copying of data from one memory location to another without CPU support. As a result, if the send operation programs the communication hardware and returns before the communication operation has been accomplished, process P1 might receive the value 0 instead of 100 without this kind of proper support. Okay. Now let us look into this diagram. So this has been taken from this book Introduction to Parallel Programming by Anand Grama, A. Gupta, G. Karipsis, and B. Kumar. So this diagram is basically for non-buffered blocking message passing operation. So we don't have a specialized buffer, hardware buffer. So if you look into this, let's say first diagram, that is A, and this is like a time axis. So from top to bottom, you can take it like time going from 0 to some finite amount of time. So this was the sending process P0. So sending process was doing something. So at this time instance, it sends or it requests to send something to the receiving process. Let's say the receiving process is P1, but it turns out that receiving process is not ready to receive that data. So the sending process basically waits. So this white segment that represents the idling time. So the receiving process is ready at this instant. So basically the sending processes has lost this amount of time because we are talking about a blocking protocol. So this has been blocked because we want to make sure that this CPU will perform something on this sending side only after it is guaranteed that the data will reach properly to the receiving process. Now, once the receiving process says that okay, now I am ready to receive the message, then the message actually goes from the sending process to the receiving process. So that is being represented by this black part. Now, once this is done, then sending process resumes whatever it was supposed to do, and the receiving process also does what it was supposed to do. So typically, this process involves a handshake between the sending and receiving process. So the sending process sends a request to communicate to the receiving process. When the receiving process encounters the receive, it responds to the requests. The sending process, upon receiving this response, initiates the transfer, and we can see that the major drawback is the this idling time, which is basically represented using this white color. So that is how a non-buffered blocking operation takes place. So the similar kind of thing can happen in another situation. So the first situation was sender comes first, and then there is idling at the sender side. The second situation is like sender and receiver come at about the same time, and then there is a very little idling. So you can see there is no white part here. So the sending process sent a request, and the receiving process was ready. They were basically very much synchronized with each other. So the moment the sending process sent that request, receiving process was ready to respond to that, and then the actual data transfer took place, and again the sending and the receiving process resumed their activities. The third situation is like when receiver comes first. So here the receiving process sent a request for receive, but the sender was not ready. So when the sender was ready, it sent a request that the message needs to be sent, and then the receiving process was already ready. So it was just undergoing some kind of idling. So when both are ready, the data is basically transferred between each other, and once the data transfer takes place successfully, then they resume each other. So the summary is that by this blocking mechanism, we are just ensuring that the data reaches safely from process 0 to process 1, that is from sending process to the receiving process, without any change to the data. The only limitation is that there is a considerable idling overheads, which will slow down the overall code. I mean, the running of the runtime of the algorithm. The next one is buffered blocking message passing operations. So here also you can see that we have a blocking protocol, but a solution to the previous limitation was that we are going to use some kind of buffer. So in simple solution to the idling and deadlocking problem outlined above is to rely on buffers at the sending and receiving ends. So what the sender does, it simply copies the data into the designated buffer, which is kind of a hardware support, and returns after the copy operation has been completed. So now the process or the CPU at the sending side is free to resume its activities. The data must be buffered at the receiving end as well. So the sending process basically copies the data in the buffer, and then in on the receiving side also it can be copied into a buffer, and when the receiving side is ready, it can get the data. Okay, so let's understand this through this schematic. So here you have a sending process. Okay, so this is the timeline. So basically, it started here, and then the sending side, some operations are going on. Exactly at this location, the sending process is supposed to send some data, but exactly at that time, the receiving process is not ready to receive that data. But you can see that because there is a buffer present, there is no idling here. So sending process simply copies that data into the buffer, and then it can continue its operations, or it can resume whatever it was supposed to do. And by doing that, it just makes sure that the data reaches safely to the receiving process. Now when receiving process is supposed to receive the data, it simply gets the data from the buffer, and then it resumes its activity. So you can say the blocking buffer transfer protocol in the presence of communication hardware at both the send as well as receive ends. Now suppose that in the absence of communication hardware, how it will be done. So here what happens, like the sending process interrupts the receiving process. Now you don't have a buffer at both the ends, you just have a buffer at the receiver end. So sending process interrupts the receiving process responds to that, gets the data copied at it buffer, and then both of them basically resumes its own operations. And then when that particular data is required by the receiving process, it receives that data from the buffer. So in this case, you have a buffer only at the receiver end. In this particular case, you have buffer at both the ends, and you can see how buffering basically helps in reducing the overall communication time. Now the third case is basically non-blocking message passing operations. So in this case, it is the responsibility of the programmer to ensure that the semantics of the send and receives are correct. This class of non-popping protocols returns from the send or receive operation before it is semantically safe to do so. So if you look into that particular example, here actually, unless we make sure that this 100 gets communicated or transferred properly to P1, it is not safe to go forward. But in non-blocking, actually we go forward. So we don't block this particular operation send. So that's why it is called non-blocking operation. So non-blocking operations are generally accompanied by a check status operation. So what do you do? We just make sure that whether the data has been sent properly or not. So there is some status checks for that. When used correctly, these are capable of overlapping communication with computation. So while the communication is taking place, the computations are also going on simultaneously. So there is a significant gain, because what happens, this communication networks has a finite bandwidth and a finite latency. So if we do not overlap these two processes, that communication and computations, and in case there is a significant amount of communication, then the overall runtime will go up. So the non-blocking basically helps in reducing the overall runtime by overlapping these two things, that is communication with computation. Message passing libraries typically provide both blocking and non-blocking primitives in the form of different syntaxes that we'll look into in the next lecture. So if you want to understand the non-blocking message passing operation, we can understand it through this particular diagram. So what is happening here? So this sending process, it requests to the receiving process that it wants to send some data, but so happens that the receiving process is not ready. So but because it is non blocking, so it does not wait, and there is no buffer also, so there is no hardware support. So it basically resumes whatever it was supposed to do, and it just waits for the receiving process to respond to its request. And so therefore this time, when instead of getting blocked, it has resumed its future operations, this is the unsafe period. So it is unsafe to update the data which is to be sent to the receiving process. So basically, if we take our previous example, so in this time period, if we change the value of a, that is definitely very unsafe, because instead of getting a is equal to 100, the receiving process might receive something different if the programmer does not take into account that particular that particular issue. So you can see the danger in this case is that there is a time when it is unsafe to update the data being sent. So you have to make sure that we do not update the data unless it is properly sent to the receiving end. We also can have another situation where we can have a hardware support in in the form of some kind of communication hardware, and then to a certain extent this unsafe time can be reduced actually. So in summary, we can see that this is the overall parameter space of possible protocols for send and receive operations. So if you look into this, so there are two options. One is blocking and second is non-blocking. And corresponding to each of these options, you have two options: buffered and non-buffered. So the first combination is buffered blocking, the second one is buffered non-blocking, the third one is non-buffered blocking, and the fourth one is non-buffered non-blocking. So in the first case, so when you have a buffer, so that is like you have a hardware which supports buffering, and you have a blocking operation. So what happens is like sending process returns after data has been copied in the communication buffer, and this helps in reducing the overall communication time. Second thing is like buffered non-blocking. So in this case, sending process returns after initiating the direct memory access transfer to the buffer. This operation may not be completed on return. So in this case, blocking, the sending process waits unless the data has been completely copied into the buffer. In this case, the sending process does not wait because it's a non-blocking. It simply initiates that process of copying the data to the buffer, but it does not wait. In the case of non-buffered blocking operation, it is the case where there is maximum idling time because the sending process blocks until a matching receive operation has been encountered. And the fourth case is like when you have non-buffered non-blocking. So the main challenge here is that um, there can be a lot of times where it will be unsafe. So programmer has to ensure that that safety, and it has to the programmer has to ensure that this communication takes place safely. Okay, so here programmer must explicitly ensure semantics by by coding in such a way that the completion of this sending receiving process takes place safely. In our next lecture, we'll go into the details of message passing interface, and we'll also look into some cases where deadlocks arise if the coding is not done properly. So see you in the next lecture.